So what'd you come up with? What were your answers for A and B? That's what we're getting ready to find out. All right, so I'm going to clear this screen off, and we're going to start with A first, and we're going to see how well you did. So for part A, again, they want you to take a molecule that looks like this, and here's a methyl, and there's a methyl, and they want you to react it with something, question mark, in order to get 2,3-dimethyl-2-butanol. Okay, so butanol. But is 4. 1, 2, 3, and 4. The 2 represents where the alcohol is at, so 2-all. So on the second carbon, I'll have an OH group. And then on the second carbon, I will also have a methyl group, a CH3 group. And then on the third carbon, I will also have a methyl group. That's why it's 2,3-dimethyl. So I need to take something that looks like this, and I need to get to something that looks like this. So how on earth do we do this? So 2,3-dimethyl, 2-butanol, and up above, that is where we start. 3,3-dimethyl, 1-butene. Okay, so it looks like we've added an OH group, right? I mean, that's really the only thing that we've done. Here's a carbon, there's a carbon. Here's a carbon, maybe this carbon is shifted, okay, but it's still there. And then 4 in the long chain, 4 in the long chain. The only thing that we've done is added an OH group. So what if we just add water and a little bit of acid? What goes on here? All right, so over here to the left, this is where I'm going to start working. We're going to see if this will give me what I want. So if we add water and acid to this alkene, the rules of organic 1 said an addition reaction is going to go forward. So the double bond's the target. 2 sides of attachment open up, one here, one there. Hydrogen plays with other hydrogens. That's Makovnikov rule. Hydrogen will go here. And then what we have left over is the OH group. All right, well, if I take a look, that forms a full carbocation. And before that OH group comes in, I have to question it. Will that move? Will that shift? Yes or no? If I look at the space of that carbocation, it knows if it can move over here to the right-hand side, then this could get into a more stable location. It's all about location, location, location. In order to do that, though, it has to switch with something. So it's got to take one of these methyl groups, and it has to shift it over and say, you're going to go there. When that happens, that's called a 1,2 methyl shift. There were 2 shifts that happen in organic 1. 1,2 hydride, which was a hydrogen moving, and a 1,2 methyl, which was a methyl group that moved. So because that's now shifted, that is the new spot that the OH is going to go into. So here is where the OH is going to go. And folks, what is that molecule? Is this molecule the same as that one over here to the right-hand side? And the answer is yes, it is. So it looks a little different, but it's not. How do I know that? Because look, it's just written backward. If I look at this molecule, the OH group is second toward the end. And if I look at this molecule, it's second toward the end. Off of that carbon, I have a methyl group. Off of that carbon, I have a methyl group. And then the third carbon down, I have a methyl. And then the third carbon down, I have a methyl. So these 2 molecules are identical, even though they look a little different on a sheet of paper. That's not a big deal. If I had to go in and name these, I could. If I wanted to name this alcohol, I number closest to the end. So there is a 1. That's the number 1 spot. So 1, 2, 3, 4. This is a butanol. And that butanol is going to happen on the second carbon. So 2-butanol. And then on carbon 2 and on carbon 3, I have 2 methyl groups. So 2,3-dimethyl, 2-butanol. And folks, look at part A. That's exactly what they want you to make. 2,3-dimethyl, 2-butanol. Now let's take a look at B. For B, it's a different type of product. All right, so what I'm going to do, I'm not going to erase the whole thing. So let me just erase this water and the acid. And over here, that's where we'll do our next template. And then, of course, here is a different product that they want me to end up with. All right, so what they want me to end up with here is 3,3-dimethyl-2-butanol. All right, so bute is 4, 1, 2, 3, 4. On the second carbon, I have an OH group. And then on the third carbon, I have a methyl, and the third carbon, I have a methyl. So look at this. This is not allowing rearrangement to take place. In the water acid addition, we saw rearrangement took place because there was a more stable carbocation spot. We want to prevent that from happening. We want to make sure that that OH group goes onto that second carbon. That's what our product needs to be ending up to be. The issue, just like before, is if we did anti-Makovnikov, that doesn't fix our problem, because the anti-Makovnikov addition would put the OH group on the left-hand side, not on this one, and that's not where we want it either. So an anti-Makovnikov is not the simple answer here. So I'm going to take our starting reagent, carbon, double bond, carbon. Here we have 3 methyl groups off of that third one. And I need to pick out a set of reagents that will allow this to go forward. So I know at this point now, if I can make an epoxide, I kind of lock things into place. The epoxide will make sure that where those carbons are going to be, that's where the nucleophiles will be as well. No rearrangement. So I need to make an epoxide, and I know that I can make an epoxide by using a peroxy acid. One of the most common peroxy acids, again, is MCPBA. So when I add the peroxy acid, what will happen is that my double bond will break. That's what we learned in the alkene reactions, and an epoxide forms. There we go. So when that epoxide forms at this point, I need to make sure that I add on something that can break that epoxide up. And I want to make sure that what I do add is going to be a base, because only then will a base come in and attack that side which is the least stable. That's the very first step in the base reaction. If I added an acid, my OH would get protonated and it would go with the more stable. It would go at the end. That is an anti-Makovnikov reaction. If I added an acid at this point, I've just ended up with the same product that an anti-Makovnikov reaction will give me. So that's not a very good decision. I need a base. That's what we did in our last example. I need a base. And that base, I don't need any other group. I don't need an OCH3. I don't need another OH. I just need a simple O hydrogen. There's nothing else on there except for the OH group. That is it. And I already have the O. So my only choice for a base here is going to be H-. And that is going to come from LAH. A lot of people just write H- there. That way they know for sure they're getting their point across. I need to add hydride. So H-. Others, they try to trick you. And they'll write LAH just to make sure that you know what needs to happen here. So when I add on the H-, the hydrogen is going to come in and it's going to attach to this side. That is where that new H is going to go. All right. That allows this bond to go ahead and break. And that oxygen now goes over to that second carbon, which is where it needs to be in our product. Now, I'm going to erase this H back off because it's understood to be there. I don't want to complicate this structure up anymore, so I'm just going to get rid of it. We know it's there. However, this oxygen is a negative at this point, right? I didn't add anything else to it, did I? No. I've only added MCPBA to form the epoxide. Then I've only added the H- to break the epoxide ring up. And now I need to satisfy that O-. So in step number 2, maybe you can do like step 1 and step 2 here. That's perfectly okay. I now need to add some type of acid onto this molecule so that way an H can go there to form my alcohol. And that's the purpose of adding acid at the very end. Okay, so we're wrapping up Organic 1 and Organic 2 into one lecture blurb, all concerning epoxides, because we did talk about epoxides in Organic 1, and that's why this creeped up the way that it creeped up. Something that I've not really mentioned too much here is epoxides can form on rings. We might have did 1 or 2 examples of those, right? So we can form a ring and we can have an epoxide that looks like this. This is not a deal. It's not a big issue. The ring still opens up. We still get things attached to the ring, just like what you would expect. We did examples with these without a problem. I didn't really put the brakes on it at that time and give you anything special. However, we're getting ready to wrap another lecture in Organic 1 into this one. I told you, it's a build-up process, folks. What we have to keep in mind here is a little bit of stereochemistry. Oh, God, it just drives people crazy when I say stereochemistry. So let's say that we add a base onto this structure. Okay, well, if I add a base onto the structure, it's a symmetrical epoxide, so it really doesn't matter, right? I mean, I've made it easy for you. The ring's going to open up. There's the oxygen from the epoxide, and then that OH is going to come on, and folks, it's going to add on to the other carbon, just like what you would have predicted. It's not a big issue, right? And then this oxygen's going to carry a minus. So if I didn't draw it that way, I mean, some of you might need to see this, and that's okay. But the epoxide, that oxygen minus could go down and the OH could go up like that. Both of these are going to happen. It doesn't really matter how you draw them. But the issue here is stereochemistry. Okay, so what I mean by that is that sometimes when that OH goes on, well, the oxygen's already here from the epoxide ring. That could be pointed towards you. This oxygen could be pointed away from you on the OH. Okay, so this is a trans orientation, right? All of this is stereochemistry. Stereochemistry, 3D. Sometimes this stuff is very important. The other version, though, could maybe flip-flop it. The OH and the O could maybe switch places here. And here the OH could point towards you, and here the O minus could point away from you. Well, in the next step, we would normally add H plus, and the H plus would allow me to take that hydrogen and satisfy that O and satisfy that O as well. So we end up with 2 OH groups. Now, is there a difference? Both of these are trans. I know that they're trans because they're pointed in opposite sides. That's something that we learned in Orgo 1. OH points toward me, OH points away from me. They're in opposite directions. And these are 1-2 spots because no matter how I name it, no matter how I number it, it is going to be carbon 1 and carbon 2. So trans 1, 2. They are di because there's 2 of them, and alls because they're alcohol. So these are trans 1,2 diols. They're also called vicinal. That was another name that we used in Organic 1. Vicinal basically means neighbors, not vicious, even though neighbors are probably vicious with each other if you get the bad ones. And another term that we like to use here, just to throw out more terminology and get used to the words, are glycols. It's just another name that we go by. Diols are often called glycols. So just as a hint, when we look at these epoxides, especially when we're locked into a ring, because rings cannot freely rotate like straight chains, right? They're kind of locked into place. Stereochemistry could be part of this description. And that stereochemistry really means which side will that piece add on to? Will it add on to the back side, or will it add on to the front side? And in this case, we get a trans orientation. So as you would expect, if this gives us trans, is there a way that we can get cis? Can we put these OH groups on the same side, not on opposite sides? And the answer is yes, we can do that. So here we will have a ring with maybe another epoxide on it. Again, it locks it into place. Stereochemistry is pretty important. So how on earth can I open this ring up? There's the oxygen from the ring. I'll eventually protonate that, right? That's what we've always done with epoxides. And in this case, maybe add on another OH group as well, but ensure that they are on the same sides now. Just a little bit of stereochemistry. That's it. That's all. Just a review. How can we do it? Well, it's a two-step process. Not very easy. It requires osmium oxide, or tetroxide, OSO4. And it also requires a little bit of peroxide, think of it going on backwards, and water. Almost like an anti-Makovnikov reaction. So the OSO4 and the peroxide and the water, that will open the ring up. I have oxygen on one carbon, freed up the other carbon. OH goes onto one spot, and a hydrogen will satisfy the oxygen on the other. This is, again, a 1,2 diol, but these are on the cis locations now because they're pointed in the same direction. That's how we do it. All right. Another way, I don't even need an epoxide here. I just need a double bond. That works as well. That double bond will break. Two sites of attachment open up. OH goes on one. OH goes on to the other. And they go on in the cis form. That's even easier. I don't even need an epoxide. I just need an alkene. That alkene, that double bond will break, and those reagents get added on, breaks the double bond, and all of a sudden I have a diol, and they're pointed in the same direction, unlike that first example that pointed them in opposite directions. Something else that I also want to mention before I stop this video is something called a crown ether. I know. We didn't talk about these when we talked about ethers. I mean, we're talking about epoxides and then we go back to ethers. I know. But crown ethers are a special type of molecule, and they are cyclic. Hence, here's the epoxides. They were circles, three ways with the oxygens. Crown ethers are cyclic structures as well, and they have several ethers that get connected together. So think of this as one ether bonded to another ether, bonded to another ether, and then these ethers kind of go around in a circle, and they just basically pair up on themselves. They make cyclic ether structures. What happens is that here in the center, we get this cavity, and these cavities are great for positive cations. Think of these as a cage. Crown ethers are caged molecules, and that cage will grab onto a cation, and that cation could then be transported across something like an organic membrane, so that way those cations can react with organics. Because here's the problem. If I have an organic molecule that I want to react with, and I add on a salt, I don't know, Na plus and Cl minus, these are ionic. These are polar. And we know that opposites do not mix together. So how on earth can I get sodium maybe into an organic layer to take advantage of it, or any other metal to take advantage of it. And crown ethers do a very good job. The reason is because the crown will circle around this sodium, and these crowns are all made up of carbon, oxygen, carbon, oxygen, carbon, oxygen, carbon, oxygen, very organic in nature. And these cages will then travel across and go into an organic layer, and then we could release that ether, break it open, and release all of the sodium out of the inside. A couple of definitions here that come along with crown ethers. The crown ether and the piece in the middle. The crown ether is called the host. You're having a party at your house. You're the host, and you invite someone in. What you invite in is called the guest. So that's what we call the inside of the crown ether. So the positive piece typically is what's inside of here. That positive piece is called the guest ion, and that guest ion or the guest molecule. It could be a molecule if it carries a full-blown positive. I mean, that could be transported well, not a big issue. That guest is now inside of the host, and eventually you're going to bust down the house and release the guest into the new environment. The whole thing together is called an inclusion compound. All right, so here's an example of what a crown ether looks like. Here I see a crown ether. It's a cyclic structure, R-O-R-O-R-O-R-O, all the way around. There's free pairs of electrons on these things, and these are negative areas. So as you can imagine, negatives are not going to do very well in the center, because this positive will venture off into the center and get trapped. And the reason it gets trapped is because it's now surrounded by all of these negative oxygens that carry free pairs of electrons. So this is the guest, this is the host, and the inclusion compound includes everything, and that sets up the caged network that it can then travel and release somewhere else. Here's a space-filling model of different crown ethers. So here's lithium that's bound with 12 crown 4. Here's sodium that's bound with 15 crown 5. And here's potassium that's caged with 18 crown 6. A couple of things I want to mention here. Notice the atom on the inside, lithium, it gets bigger to sodium, it gets bigger to potassium. And as the atom gets bigger, well, the ether has to get bigger as well. So the bigger the atom, of course, the bigger cage that it needs to transport it. A couple of things about the crown. 12 crown 4, what does that even mean? Well, crown is this whole concept that it goes in a circle. So that is a crown ether. That's a functional group. The 4, what does that mean? There's 1 oxygen, 2 oxygens, 3 oxygens, 4 oxygens. That's what that means. And then the 12, what does that mean? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. It's the total number of atoms in the chain. So we have an oxygen, and off of that oxygen, we have 2 carbons. There's our ether group. On that carbon, that gets hooked up to another oxygen that's connected to a carbon. There's a second ether group, and it continues on into a circle. So sodium gets bound up in 15 crown 5. So I've got 5 ether molecules basically. 1, 2, 3, 4, 5. There's my 5 oxygens. 15 in total. So if this is start at number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 crown 5. All right, so there's the crown ethers. That's how we name them. That's what they mean. So here's another example of crown ethers, and what I do want to say is that there is purpose in these. We just don't utilize them that much, and people are still doing research with crown ethers and trying to figure out what are the best possible scenarios to use these in. But up here at the top is a very good example of why we would use a crown ether. So here we have an organic molecule, has a bromine on it, and this is called 1-bromohexane because there's 6 carbons in total. And then here is a salt, and this is sodium cyanide basically, or sodium nitrile. It goes by either name. And this salt is an ionic compound. So the question really has always been, how do we get this negative piece that we want in solution to work out with this organic? If this is ionic and this stuff is soluble in water or an aqueous solvent, how do we get it in an organic solvent instead? And these are always one of the problems that we have when it concerns some of these reactions. So one of the ways that we can do this in order for this reaction to go forward, a substitution reaction is going to happen, right? This negative carbon or this negative carbon in the nitrile will come in and attach to that carbon, forcing that bromine to leave, and we get a substitution reaction happen. How do we do that? Well, one of the ways that we could get the nitrile in and the sodium in to solution to keep it separate, to make sure these reactions go forward, is the use of a crown ether. So if we can capture the sodium, and if we can make sure that this sodium stays in the crown ether, then this will free up the negative nitrile group, so that way it can act as a nucleophile and replace the bromine. Otherwise, there is a chance that when this breaks apart, the sodium can come back onto the nitrile, and after that point, the nitrile is not going to want to do anything because the sodium is there to balance that charge. Okay, so that's where this video is going to stop. A little bit about epoxides, a little bit about synthesis, crown ethers pop back up, and ring structures popped back up as far as epoxides go. So we are moving on. And what we're going to move on with next, in the next section, if you look at this, alcohols, check. Ethers, check. Epoxides, check. Oh, no, not really. We're not done with epoxides yet. So there's one more type of epoxide that we need to talk about, and this is going to be called an arene oxide. So it's very similar to epoxides. We're not going to do a lot of reactions with them. Phew, thank goodness. Wipe the sweat from your forehead. We're not going to do them. But we at least want to bring them up into a conversation, talk about what an arene oxide is, a little bit about what it does and how it's relevant to you before we move on to amines and the sulfur-containing groups at the end of the chapter and the end of the lecture. All right, so in the next video, we'll pick up here. We'll finish off epoxides with the discussion of an arene oxide. So an arene oxide is A-R-E-N-E oxide. All right, so I'll see you next time. When you hit the play button, I'll be here. I'll be waiting. I'll be ready to go, and I hope that you're ready to go too. I know. When is it ever going to end?